In this lesson, we shall answer question 6. Right, in South Africa, the transportation of goods by trucks adds to the traffic problems on our roads. A 10,000 kilogram truck travels up a straight inclined road of length 23 meters. We can see it's 23 meters over here. Right, at a constant speed of 20 kilometers per hour, the total work done by the engine of the truck to get there is 7 times 10 to the 5th power joules. The work done to overcome friction is 8,5 times 10 to the 4th power joules. And we are saying calculate the height h reached by the truck at the top of the road. Okay, let us look at these and answer the question. Right, to answer the question, there are a couple of things that we need to take into account, but we take into account that to find the height that the examiner wants, we need to recognize that work done by non-conservative forces is actually equal to the change in potential energy plus the change in kinetic energy. Okay, so that in the end, what we have is work done by non-conservative forces is the same as what? Right, it is the same as mg. And mg what? Now, mg, now you can put here the final height minus the initial height plus. And then here, what you then have is the following. You have half m v squared final v squared initial. We want to find this height h reached by the truck right at the top of the road. And therefore we recognize something, that the total work done by the engine of the truck to get there. Now, the couple of things you need to look at and I need to emphasize here today, it is the fact that as the truck is moving up the incline, there are two forces of interest. There is friction. So there is work done to overcome friction. Friction is in the opposite. So the truck is at a point here, and when it is at this point, there is friction in the opposite. Simultaneously, there is what you call the applied force upwards there. But the truth is, the applied force is much bigger than friction. And therefore, you need to look at the fact that the total work done by the engine of the truck to get there is this. And this work is bigger than what friction is doing. Because if ever the engine was not powerful, the truck was not going to get to the top. So because the engine of the truck is powerful, exerting more force than friction, we are sure, therefore, the truck was able to get to the top of the road. Here is our story. Then here we have 7 times 10 to the 5th power minus 8,5 times 10 to the 4th power, because the friction is weaker. So we subtract the friction. And this is therefore equal to the mass of the truck. What is the mass of the truck? It is actually exactly 10,000. Right. Now, what is the final height? Final height is h. The initial height is 0 at the bottom. There was no height when the truck started. And then we continue with the rest of the things here. And let us clean this up a little bit. Right. Okay, so you continue. Right, so we have here with us half the mass. The mass is 10,000. And therefore, you have the final velocity minus the initial velocity. The final velocity of the truck is equal to the initial velocity of the truck, and it is 20 kilometers per hour up the incline. Okay, now this is 20. Now the kilometer is the same as what? Is the same as 10 to the 3. That's 1,000. And you divide by the hour. The hour has 60 by 60 because 1 hour is made up of 60 minutes by 60 seconds. 60 minutes by 60 seconds. And this is therefore what you get. And when you get this here, you are able to get the 5,56 meters per second, which is 5,56. Then you square the initial and you square the final. And what we're able to see is the fact that at this point, the final velocity and the initial velocity of the track is the same. And therefore, it all gets down to zero. Now, because it gets down to zero, we are in business anyhow, because it really simplifies our lives in a big, big way. And therefore, now what then do we achieve next out of these? We're able to realize that this whole chunk here, this whole chunk goes to zero. And when that goes to zero, what then are we able to achieve out of this? Right, and we do the subtraction. Right, when we do the subtraction, subtract these two guys, and when we do, it becomes 6,15 times 10 to the 5th power. And this is equal to exactly 10,000. Right, okay, yeah. It's exactly 10,000, but please watch out here. Watch out here, because we have 10,000 multiplied by, which is 10,000 times 9.8. And we then have the height h minus 0. Right, so we have the height h minus 0. That's what we have. And we add all these things here. So yeah, just take note of the fact that this is going to be the mass times 9,8 times the height. So here we have this times 9,8, and now the 9,8, and you multiply everything by the height. You can use the comma, decimal comma, just to be consistent, using commas everywhere. Right, and therefore it is 9,8, then we have the height. And then at this point, you continue to do the simplification, and we're able to see, therefore, that we're going to have that the height, h, is 6,15 times 10 to the 5th power, divide by 10,000 times 9,8. Times 9,8. And then now you use a calculator to get the result. And what we're able to get here, it is actually 6,28 meters. Right, and therefore the height that the examiner wants will actually therefore be approximately. Right, so the height the examiner wants is therefore approximately 6,28 meters. Like so. And this is the height h reached by the track at the top of the road here. This height is approximately 6,28 meters. Right, where's the question? It's a recap on this, because I know very well that this was discussed yesterday, so, but yeah, I'm trying to, I brought new questions on this, so I'm sure that you learned something today. This section is on work, energy, and power, because you must also learn how to calculate the instantaneous power delivered by the engine of the track. I'll give you a homework at the end of this discussion. Right, in the absence of a question, we'll move to the next question. The next question is about calculating the instantaneous power delivered by the engine of the track. Right, what is the instantaneous power? Now, for us to calculate the instantaneous power, there are a couple of things we're gonna, okay, because if you need to calculate power and we have velocity, we use the formula power equals force times velocity. Okay, that's what we use. And so at this point, we can see that we do not have the required force because instantaneous power delivered by the engine of the truck, we need the force that the engine of the truck is applying to have the truck moving upslope. So we use the formula to find the force that this engine of the truck is applying. So you're going to use F delta X cosine theta. Okay, because when the truck is moving somewhere there, a couple of things are happening. We have the weight, that is, you have the normal force, you have the force applied by the engine because it's moving upwards, but also you have what you call the friction force that is actually downslope there. So these are the kinds of obviously interacting forces that are involved. But now, obviously, we're interested in finding this guy, this force. What is that force there? Right, so we're going to find it together just now. Let us calculate it. So now, what then is the next thing that we need to do here? Right, so we need to calculate it. Fellows, what is the work done? Okay, how much work, the total work done by the engine of the truck to get there, the work done by the engine of the truck to get there is 7 times 10 to the 5th power. And this is the same as F force. 23 is the delta X. And then we have the cosine of 0 degrees, because what is happening here is that when the truck is moving upslope, you have the delta X. Delta X is in that direction and the applied force is in the same direction. So the angle between these is actually 0 degrees, which is the angle theta. That's why here we're putting 0 degrees, because the applied force and the delta X are both parallel to the slope. And therefore, the angle between them is 0 degrees or 0 radians. And therefore, we have these. Now, we are interested in finding the force. So what is the force at the end of this? So to find the force, we perform division. So we take the 7 times 10 to the 5th power. We divide everything by just 23 times 1, because cosine 0 degrees is 1. You should divide 7 times 10 to the 5th power by 23 times 1. We have 3,04 times 10 to the 4th power newtons. Okay, so now as a consequence, we have this, but yeah, we can quickly be in a position to find the required power in green. So power is force times velocity. And therefore, what is the force? The force is 3,04 times 10 to the 4th power, right? And therefore, that is the force, this one here. And therefore, what is the velocity? The velocity of the truck, you already know, it's actually, 20 kilometers per hour. So if it is 20 kilometers per hour, we take the 20, we multiply it by 10 to the 3 because of the kilo. Kilo means 1,000. And you divide everything by what? By 60 by 60. And because it's per hour, and 1 hour has 60 minutes by 60 seconds each year. So we have that. So now what then do we get at the end of this? So we use our calculator to compute, and using our calculator, we're able to see therefore that this is 1,6 times 10 to the 5th power watts. Right, so because we had to calculate the instantaneous power delivered by the engine of the truck, right, by the engine of the truck, and therefore the instantaneous power delivered by the engine of the truck, or the engine of truck, is 1,6 times 10 to the 5th power watts. Where's the question here? Who does not understand something? Who has an input to make? Where's a contribution to make? Who's saying, okay, but I think the number there must be 5 and not 6. It must be this and not that. I think this and that. You let me know, please. Okay, you let us know. You share your answer, because in the end, this is what we're learning. I'm going to send a homework on the WhatsApp group at the end of our discussion. You take the homework, you practice during the day tomorrow, because it's night, obviously now. I know that you're tired and you have other projects to do. Okay, so that is why I actually obviously give you the homework, and then you can do it during the course of tomorrow. Right, so we continue. We continue. Right, so let's speak about the arrestor beds. The arrestor beds are constructed as a safety measure to allow trucks to come to rest when their brakes fail whilst going downhill. Now, when the trucks go downhill, sometimes the brakes fail. When the brakes fail, write down two design features of such arrestor beds. These arrestor beds are very, very important. But now we then say, what are the design features? This is what you need to know as part of the curriculum. So now you need to know that the surface, right, the surface, okay, I'm just write clearly here. So we are effectively saying here the surface, right, must provide, just put a dot here, must provide sufficient friction, must provide sufficient friction, like sand, right, like sand. Okay, you'll forgive me if the network is disturbed a little bit, but this is recorded. Right, must be long enough. Right, must be long enough. Right, for the vehicle to stop. For the vehicle to stop. Right, surface must provide sufficient friction like sand. Must be long enough for the vehicle to stop. Right, so this is what must, these are sort of what you call the design features of the arrestor beds. These arrestor beds, which are used to assist in stopping trucks in the event that the brakes fail. The surface must provide sufficient friction. These arrestor beds must provide sufficient friction, and normally sand is put there at the toll gates, etc. And on actually what you call steep slopes. When the trucks go downhill, you see that at the toll gates, etc. It's often the case that you see these stretches of paths with sand, and now the surface must provide sufficient friction like sand for the truck. Then you put it into sand, into a surface, and it's sand. And if it has sand, then the sand is going to provide sufficient friction for the truck to stop. Must be long enough for the vehicle to stop. This sand must be of the required length. This arrestor bed must be of the required length to make sure that the truck is able to stop. Okay, we look at the next question. Right, a loaded truck with a total mass of 5,000 kilograms travels up a straight incline at a constant velocity of 15 meters per second. Here is a giant truck. Okay, now I want us to work together in doing this question. So please, please, guys, you need to be very, very alert. Right, I want us to work together in doing this question. So you must be very, very alert. This loaded truck with a total mass of 5,000 kilograms travels up a straight incline at a constant velocity of 15 meters per second. Here's this giant truck. At 15 meters per second, it's going uphill. At the top of the incline, the truck is at a height of 55 meters above its starting point. The work done by frictional forces is 8. Okay, you see, the examiners are doing the same thing. And they are giving us the work done by frictional forces, and it is 8,5 times 10 to the fourth power. Ignore the rotational effects of the wheels of the truck. Define power in words. Who can define power in words? Anyone? Quickly. What is power? What is power? What is power? Who knows? What is power? Tando, what is power? Tando, what is power?
So I think it's the ability or like to do something,
Okay, that's fine. So power is
the
the rate.
ability or capacity.
Yes, okay, I understand. Yeah, it is the rate at which work at which work is what? Is done. Power is the what? Is the rate at which work is done. Okay, so that is right. So we continue. We continue. Right, so power is the rate at which work is what? Is done. Right, so, but also this is not the way to define power. Power can also be defined in many ways. Yeah, I'm in class at the moment until 10 p.m. Right. Yeah, so yeah, if possible, please give me a call after 10. Yeah, it's problematic. Yeah, it's problematic. Yeah. Yeah, it's not good. Yeah. Yeah, okay, thanks, Kakul. Okay, thanks. Right, so the rate at which work is done, and then now it's not the only way to define power, and there are many ways. You can also define power as follows. So you can define it like that, or you can say it is the rate. Power is the rate at which energy is transferred. Is the rate at which energy is transferred. Okay, so this actually is the fundamental definition of power. Okay, so now it's very important that you understand this, Tando and Nombuso, right? That if you are dealing with power in physics, it can be defined as the rate at which work is done, or it is the rate at which energy is what? Is transferred. Okay, so this is the fundamental definition of power, and this is how you need to define power in examinations. Okay, so power is the rate at which work is done, and it can also be defined as the rate at which energy is transferred. Now, I want us to continue and look at the what you call labeled free body diagram, showing all the forces acting on the track as it moves up the incline. Okay, this track is actually going up the incline at a constant velocity of 15 meters per second. Now, we are then asking the question, what is the labeled free body diagram showing all the forces acting on the track as it moves up the incline? And we draw the diagram together. We continue. Right, so if you look at 5.2, we proceed as follows. Right, a couple of forces are actually at work here. So when the track is going up the incline, you need to understand that there is what you call the weight of the track, but also there is, because there is what you call work done by friction forces, and therefore there is what you call friction that is in the opposite, but you also have what you call the applied force that is going uphill like this, and you also have the normal force, that is the force that is exerted by the surface on the track. Okay, so that is something that is extremely important for us to take note of. So the labeled free body diagram would actually be shown by using the dot and arrows. So you have the weight this way, you have the friction force in the opposite direction, opposing the motion upslope. You have the applied force, and you also have the normal force by the what? Normal force by the surface on the track. Any question on the free body diagram showing all the forces acting on the track as it moves up in the incline? I'm going to give you homework on this. Please, you must understand these things, because I'm going to give you a homework on the group, and you must be able to solve the homework on the group. So these are the things that you need to learn. Okay, and so it's very, very important there to find the to determine the calculation over here. Okay, so we continue to do more and solve more of the problems here. Right, so we proceed as follows. Right. No question. In the absence of a question, we actually proceed um, um, to do the next problem. Right, obviously we still have the track, and the track is still going uphill at a constant velocity of 15 meters per second. But we need to use the work energy theorem to calculate the work done by the engine of the track to get to the top of the incline. Now, the work energy theorem must be used here, and the work energy theorem is known very well. A couple of things, therefore, remain very important. What then do we do here to solve this problem on the work energy theorem? Right, so we are doing 5.3 at the moment. The work energy theorem states that W net is equal to the change in kinetic energy. W net is the change in kinetic energy, and this is what we call the work energy theorem. What then do we do with this? We continue to solve, but even more problems on this. And we analyze what is happening as this track is actually going uphill this way at the constant velocity. Right. What? So the examiner is saying we could use many other things, but he's saying please use this formula. And this is what you call the work energy theorem. W net equals the change in kinetic energy. This is called the work energy theorem. Now, and we want to use it to calculate the work done by the engine of the track to get to the top of the incline there. So there's actually work. Now, a couple of things, therefore, are very, very important here. So you have the block like this. And okay, here's the track. Is it going? It's going up. It has obviously some wheels, and we're able to note a couple of things. That this track has its weight. This track has a normal force. This track has an applied force. This track has what is experiencing friction in the opposite direction. But now, the couple of things that are very important. So in the end, then it goes down like this. Right, it goes down that way, and also it goes down this way. So what then do we have? So you have the perpendicular component of the weight and also the parallel component of the weight. As much as opposite as it is going up here like this, you have the normal force there, and rather the weight that is going actually that is straight down, and you have what you call the angle there, and this angle is an angle of 90 degrees over there. Right. So what then do we have here? So we come here and we then say here we shall have there is work done. Now the net work actually here is the work done by the applied force F, and because the track is successfully going up here like this, but there's also work done by friction. We add the work done by friction, but also we add to this the work done by the weight, and this is equal to what we call EK final minus EK initial, like this. So which means you shall have work done by the applied force minus the work done by friction is 8,5. So this is then the same as 8,5. Right, so it is 8,5 times 10 to the fourth power. Right, plus. And then what is the Okay, because you know very well, it's here. Work done by frictional forces is this. So work done by frictional force is that. So we subtracted from the work done by the applied force. Why? Why do we subtract? We subtract because the applied force is so powerful but so strong that it's able to carry the truck uphill. Whereas friction now is in the opposite direction, but it's so weak that it's unable to stop this truck, and the truck is able to go up even when friction is opposing the motion. Right. So now you have the work done by the weight. Right. So the work done by the weight now is going to be exactly this work done by one component of the weight. And it is most certainly the parallel component of the weight. And if therefore this is the angle theta that we have, for instance. Okay, so let us first obviously consider the calculation first and foremost. So now what formula do we use here in the calculation of the work done by the weight? So you'd note therefore that this is going to be the mass times the gravitational acceleration times the height times the cosine of 180 degrees, or that way. You can put theta there. Okay, so I want us to analyze and look at what this means in essence, right? So we understand that since the speed is constant, the change in the kinetic energy is going to be zero, because the speed is constant. But you can do, you can put a couple of things here. You can come here and say, what is this? Is half m v final squared v initial squared. Right, so, which means work done by the applied force is 8,5 times 10 to the fourth power plus the 5,000 kilograms. So you have 5,000 kilograms times 9,8. Right, multiplied by the height, 55. Cosine 180 equals 1/2. The mass is actually 5,000. You just put in the figures here. And therefore, the speed of the truck, or the velocity of the truck, is 15 meters per second. So it's squared here, 15 squared. And therefore, obviously, this 15 minus 15 squared is actually a big zero. And so what then do we do at the end of this? So we take this and we are able to simplify these, and this will become zero. And therefore, it means that work done by the applied force is actually 8,5. So we move this one to the other side, times 10 to the fourth power. Okay, then we subtract this one. Right, so you can put a minus here. Right, let's put a minus there. So you subtract, therefore, 5,000 times 9,8 times 55 times cosine 180 degrees. So in the end, then we use the calculator to subtract everything here. And if we use a calculator to subtract everything, we get 2,78 times 10 to the sixth power joules. Right, so this is actually the work done, calculate the work done by the engine of the truck to get it to the top of the incline. It is actually the work done by the truck to get it to the incline. Now, there are a couple of things obviously here that are very, very important and that we need to take note of, right? And so we need to obviously be very, very considerate of the fact that this is very, very essential, right? And the fact that at this point, as this truck is moving uphill this way, you actually have what is actually happening here. There are a couple of things that are very important, like here at this point, where when there is a change in the work done by the weight, when there is a change in the height, right? So the change in the height, there was zero height here, and the height here was obviously 55 meters, as a matter of fact. And therefore, you are able to see that the angle that is required here is an angle, obviously, of 180 degrees, as a matter of fact. Right. And that is something that you need to take into account and make sure that you are able to interpret that very, very well. Okay. And you're able to sort of understand there. Okay. So that in the end, then we have the work energy theorem, and has been used to calculate the work done by the engine of the truck to get to the top of the incline. And it is 2.78 times 10 to the 6th power joules. Okay, think about this and make sure that you understand these, because it's very important for you to understand these. In the absence of questions, we shall recap on this if somebody has a question or something they do not understand. Let's look at the next question. Right, the next question is 5.4. In 5.4, want to calculate the average power delivered by the engine of the truck if the truck takes 60 seconds to reach the top of the incline, but we want to find the average power. What is the formula for average power? Let us use the correct formula here to calculate the average power. What is the formula for the average power? Right, so we have defined power, but the average power is W divided by change in time, and this is actually 2.78 times 10 to the 6th power. We have already found the work, and it is exactly this. Right, so the work we got here is 2.78 times 10 to the 6th power joules, and therefore we put 2.78 times 10 to the 6th power joules divided by the time, the change in time. But we're told that if the truck takes 60 seconds to reach the top of the incline, so it takes 60 seconds to divide by 60, and therefore this is the same as a 4.63 times 10 to the 4th power watts. What is the power? The power is 4.63 times 10 to the 4th power watts. This is exactly what we have. And this is the average power delivered by the engine of the truck if the truck takes 6 seconds to reach the top of the incline. If it takes 60 seconds, it's like it's just taking only 1 minute to reach the top of the incline. Okay, this is the formula we use to calculate power. And we used another formula to calculate power before. We used force times velocity. Here we're using work done divided by change in time. Okay, so yeah, these are the things that make us click in physics. So yeah, take note of this. Next question. Right, so the next thing that we're going to do now is to look at the fact that the truck now returns down the same incline with a constant velocity of 15 meters per second. Here's the truck, it's going down again. Well, it's going down because it was going up before, but now it's going down. But it's going down at the same speed of 15 meters per second. How will the work done by the engine of the truck, or how will the work done by the engine of the truck, yes, on reaching the bottom of the incline compared to that calculated in question 5.3? Write down greater than, smaller than, or equal to, give a reason for the answer. So we are having this question in front of us, but we are told here that this truck now returns down the same incline with a constant velocity of 15. How will the work done by the engine of the truck on reaching the bottom of the incline compare to that calculated? Okay, how will the work done compare to the one calculated? Will this work done when it's going down? Will the truck do less work? Which one is easier? To go down? Is more work done when it's going down or when it's going up? Which one is easier? To go uphill or to go downhill? Which one is easier? Okay, so we actually obviously look at that question. And we're able to note that the work done by the engine of the track on reaching the bottom of the incline, um, right, compared to that calculated in 5.3. In 5.3, right, in 5.3, we understand that it was going uphill. But right now, it is going downhill. Because it is going downhill, this track, what does it mean? It means that it is easier to go down than for the track to go up. Because to go uphill, hey, if you go up the stairs, it's more difficult than to just go down. So it's easier to go down. And therefore, now we are supposed to choose here, and the correct choice would have to be smaller than. So we gonna say it is smaller than, right? It is exactly smaller than. Take note of that. So we are then saying, how will the work done by the engine of the track on reaching the bottom of the incline compared to that calculated in 5.3? Write down greater than, smaller than, or equal to. Give a reason for the answer. Right. So it will most certainly be what? It will certainly be smaller than, because it is much easier to go down. But let's give a reason for the answer. So the reason for the answer will actually be that the weight, or what we call the gravitational force, right, or the gravitational force does positive work on the track, right, on the track. So the weight or the gravitational force does positive work on the track. It certainly does positive work on the track. And as a consequence, what we're then having here is therefore that you're going to have smaller than, because the weight or the gravitational force does positive work on the track when it's going down. It's doing positive work on the track when it's going down. And it's sort of the fact that, obviously, I mean, it is sort of assisting the track to go down. It is moving downwards, and also sort of the work is positive work, because it is sort of assisting the track to go down here. Okay, so that's something that is extremely, extremely important to take note of over here. Okay, let's continue to solve more problems. Okay, now here we're looking at this question, but this question is about a 3-kilogram block slides at a constant velocity of 7 meters per second along a horizontal surface. It then strikes a rough surface, causing it to experience a constant friction force of 30 newtons. The block slides 2 meters. Here is 2 meters. It slides 2 meters under the influence of this frictional force before it moves up a frictionless ramp inclined at an angle of 20 degrees to the horizontal before it goes up here, up this ramp inclined at an angle of 20 degrees to the horizontal, as shown in the diagram below. Right, the block moves a distance d up the ramp before it comes to rest. So it moves just the distance d up the ramp before it comes to rest. Show by calculation that the speed of the track at the bottom of the ramp is 3 meters per second. So now we need to show that by calculation that the speed of the block at the bottom of the ramp is 3 meters per second. So let us look at this one here and make sure that we are able to answer this question, and we are very much understanding here, and we are very, very smart. So yeah, let us do this calculation here. Way, way too easy. Right, very, very straightforward to do this particular calculation here. Right, now a couple of things therefore remain very important. So something that we can use, there are many ways obviously to do this particular calculation. The easiest way to do this is to actually use W net. So we're doing 5.1 and we're going to use W net. Right, so W net equals the change in the kinetic energy. Okay, what is the W net? If delta x cosine theta, which is half m v final squared minus v initial squared. All right, so now look at this, my friends. What is this? So we need to be in a position to have the correct interpretation of this. What is the net force here? You need to show by calculation that the speed of the block at the bottom of the ramp is this, just at the bottom of the ramp. So now the net force, what force is the net force? Okay, now there is a constant frictional force of 30 newtons, which means therefore you'd have 30 newtons here. 30 newtons. And therefore the delta x is 2 meters. Here is delta x. And we are sure that the frictional force, which is the net force, is which is the only force quite acting on this, because it's just gonna sliding this block. It's sliding, yeah. So now you take note of that, and then let us do a couple of more things here. Let's write more. And then now you have the, what else do you have? You have the cosine. Okay, what is the angle now? As it slides down here and friction is the only force that is acting there in the opposite direction, and sort of the net force there. So now at this point, and obviously it is our frictional force, but it is the net force. Now, the displacement is in that direction, so delta x is in that direction. The angle between these two here is 180 degrees. It is the angle theta, and therefore what we have here, it is cosine 180 degrees. So, and this here is half times the mass, and we know that it is a 3 kilogram block, so you put 3 here, and you have the velocities that you need to most certainly calculate. So what is the final velocity? So it will be the final velocity because you already know the initial velocity. Let me just clean this up. Okay, looks a bit untidy and it's okay, but yeah, let's just, now we have the final velocity. So what is the final velocity? Right, so the final velocity at this point is 3. Right, so anyway, we need to show that it is 3, so we're gonna put v final. What is the initial velocity? The initial velocity is this one, so it is v initial, and it is 7 squared. Right, so what is 30 times 2? 30 times 2 is a big 60, but cosine 180 is a minus, so it's minus 60, and this is exactly the same as what? Right, so you have 3 out of 2, it's 1.5 v final squared minus, which is 73.5, which is 1.5 vf squared, which is, you bring the 70 and subtract 60 from it, it will be a 13.5. And then if you take your calculator and you divide everything, you'd have that vf is 13.5. Right, which is exactly 13.5 divided by 1.5. Okay, and then if you divide these things here, what do you get at the end of this? You get exactly 9, which is vf squared here. It's 9, and therefore, if vf squared is 9, then it means that vf squared is 9. You apply the square root on both sides. Okay, remember that want the speed. So yeah, we only taking the positive here, which means the final is actually 3 meters per second. 3 meters per second, like that. And that is the answer. That is the answer. That is the answer. 3 meters per second. Exactly 3 meters per second. Now, obviously, there's a couple of things that you need to learn. And this is what we've done. So ask if you have a question. So yeah, once again, this is just a speed. So speed has no direction. So it is 3 meters per second. No direction associated with it. The actual cosine here becomes the cosine here, which is the actual angle between the force and the delta x. So we can see therefore that when this is moving here, the delta x is going to be in that direction, but friction is in the opposite direction, and therefore it is in the opposite direction, and now it is opposing everything, and therefore the angle between them is there. It's like that adjacent angles on a straight line, and that is actually the same as theta equals 180 degrees, and that is the answer. We look at the next thing. We look at the next thing. Next thing. Right. So now in the next question, it's still the same. The block moves up a distance d up the ramp before it comes to rest. Okay. It's sitting there now and it's resting there. Okay. Draw a free body diagram to show all the forces acting on the block in a direction parallel to the incline whilst the block is sliding up the ramp. Right, so we need to draw a free body diagram showing all the forces acting on the block in a direction parallel to the incline whilst. Remember, it's rough here. Right, if it is rough here, but right. And then now it then strikes a rough surface, causing it to experience a constant frictional force of 30 newtons. The block slides 2 meters. 2 meters here under the influence of this friction force before it moves up a frictionless ramp. So this one is frictionless. It is frictionless. Okay, if it is frictionless, what does it mean? It means that there's no friction as it moves up the incline. Okay, in the absence of friction, what then do we do? What then do we do here in the absence of the friction? In the absence of the friction. Okay, so we need to draw the free body diagram. So now to draw a free body diagram showing all the forces acting on the block, right, acting on the block in a direction parallel to the incline. So yeah, what you need to do is, it is this, and it is only the parallel component of the weight that is going to be acting down there, because as it slides, right, as it slides up the ramp, sliding up the ramp, you're going to have only this force because it's smooth. There's no friction. So it's only this force, but also it is just sliding this block. So no one is pushing it. So there's no applied force in terms of somebody pushing it. So the only force acting is this one. So you can draw it like this, or you can also draw like this and then say, here is this, and it is going down, and it is this parallel component. And obviously the examiners will therefore obviously mark for you here, and this would just be about 2 marks, and therefore they would actually indicate that this is that, and the label of the force, because you need to draw a free body diagram showing all the forces acting parallel, all the forces acting on the block in a direction parallel to the incline whilst the block is sliding up the ramp. Yeah. So the force is only downslope. Now, in 5.3, you need to perform a calculation. Calculate the distance d the block Right, right. Calculate distance D, the block slides up the ramp. So we're interested now in calculating the distance D. How much is this distance? Now we're interested in knowing how much is this distance as it goes up like this. So we're gonna do 5.3 now. And we continue to analyze these, but to analyze these very, very carefully. Now, we're going to then say we can use the work energy theorem, right? In using the work energy theorem, there are a couple of things that you need to take into account and then say W net is equal to the change in the kinetic energy. This is the work energy theorem. Use this formula. Right. So as it slides up the ramp like this, we've already seen that there's only one force that's going to be acting down. So which means we're going to have, okay, right. So you're going to have obviously the work done, which is W net. So you're going to have you can call it let's call it like this. Let's use the W parallel formula. You can use FG parallel, but let's just use W parallel delta X, and then cosine theta equals half m v final squared minus v initial squared, like this. So what is this? Okay, so you need to look at these and think very, very carefully of what is happening here. And as it's sliding up the ramp like that, we agreed that this is the only force that acts. And what is this only force that acts parallel to that? Because we know very well that this is going to experience a weight like this, and therefore this weight is going to have its components like this: W perpendicular and W parallel. And you have therefore that this angle here is the angle theta. So that in the end, this angle of 20 degrees is going to be sitting there as the angle of 20 degrees there. Okay, right. And now that is the delta X here is therefore going to be D. But the question is, what is this W parallel? The W parallel, you can use anything, is opposite over hypotenuse. Opposite over hypotenuse. So you're going to use the sine of theta, which is the opposite over the hypotenuse. So yeah, W parallel over W, which means W parallel is W, the sine of theta, which means that W parallel becomes W sine theta, right? This is the W parallel component, and this is delta X cosine theta is half m VF squared V initial squared, which means you're going to have the following here, right? We're going to have the weight. What is the weight? The weight is mg. Mg sine theta delta x cosine theta half m VF squared V initial squared. What is the mass of this? So the mass is 3 kilograms. 3 kilograms times 9,8 times the sine of theta, the sine of 20 degrees. Okay, so yeah, 3 is the mass, 9,8 sine 20 times delta x. Delta x is d. The distance is going to travel, it's d times cosine. So this cosine is the cosine of the angle between the W parallel and delta x. So W parallel is downslope and delta x is upslope. And we can see therefore that the angle between them is actually an angle of 180 degrees, like this, okay? and this is half. The mass is 3, and then you have the final velocity. Okay, before it comes to rest, so the final velocity is 0 squared, but at the bottom of the ramp, it is 3 squared. We have the velocity of 3 squared. Right, so now what then are we able to get at the end of this? Right, we're able to get at the end of this, therefore, that in this case, we shall have to just solve this with ease. So let us solve it here now. Want to find the numerical value of d, and we find it here. And we're able to then say d is equal to, right, which is 1.5 minus 9, which is 3 squared. And then you divide everything by 3, okay? Times 9.8 times sine 20 degrees times cosine 180 degrees. So we are having this here, and we're dividing by 3 here, 9.8 sine 20 degrees cosine 180. And therefore, d is equal to what? Right, so d is 1,34 meters. D is therefore 1,34 meters. So obviously we're interested in knowing the distance d the block slides up the ramp. So we know that we have found therefore that d is 1,34 meters. 1,34 meters. 1,34 meters. 1,34 meters. So we continue to solve more problems. We continue to solve more problems. Right. I think that what I'm gonna do is let us continue. Let us continue with the next question. The next question is about an electric motor. Right, an electric motor pulls a 20-kilogram crate from rest at point A up an inclined plane by means of a light, inaccessible rope. Okay, here's an electric motor. It's pulling up this 20-kilogram crate by means of this rope. The inclined plane makes an angle of 18 degrees here with a horizontal. B, C, and D are points on the inclined plane. B, C, and D are points on the inclined plane. The distance between points A and C is 15,6 meters, as shown in the diagram below. Okay, we're good. We're so good. Right, so as good as we are solving this particular problem here with much simplicity and ease. Right. Okay, points on the inclined plane, and the distance between points A and C is 15,6 meters. 15,6 meters, as shown in the diagram below. Okay. The motor exerts a constant force of 96,8. 96,8. Parallel to the inclined plane on the rope. A constant frictional force of 13,5 newtons acts on the crate as it moves on the inclined plane. Define a non-conservative force. Right. Who can answer this question? What is a non-conservative force? Anyone? Tando, what do you think a non-conservative force is? Or Nombuso? What is a non-conservative force, Nombuso? What is a non-conservative force, Nombuso? Okay, all right. I'm going to define that. So we're looking at 5.1. Right. A non-conservative force is nothing other than, so we say, does anyone want to try? No. Yes. Okay. A force, right? We say a force is non-conservative, right? A force is non-conservative, right? It is non-conservative. Non-conservative if the work, it does, right? If the work it does on an object, right? If the work it does on an object, right? If the work it does on an object, which is moving, if the work it does on an object which is moving between 2 points, it depends, right? It depends on the path taken, depends on the path, taken. So a force is non-conservative if the work it does on an object which is moving between 2 points depends on the path taken. So that is called a non-conservative force, right? But also it can be stated in many ways. And I want to also give the following statement of a non-conservative force here. We can also say that a force is non-conservative, The force is non-conservative if the work, right, a force is non-conservative if the work it does, in moving, right, in moving an object, around a closed path is zero. A force is non-conservative if the work it does in moving an object around a closed path is zero. A force is non-conservative if the work it does in moving an object around a closed path is zero. So that is what we have. A force is non-conservative if the work it does in moving an object around a closed path is what? Is zero. So yeah, you can either choose the red part or the green part, but you have what you call a conservative force definition there. Right, so let's look at the next point. Now we're going to look at 5.2. Use energy principles. Energy principles to calculate the speed of the crate when it reaches point C. Right, now when it reaches point C, what is the speed of this crate? Because an electric motor pulls this motor is pulling it up, is pulling this 20 kilogram crate up the slope. And now the examiner is saying use energy principles to calculate the speed of the crate when it reaches point C. So now it means, therefore, you will use the energy principles, and this is what you're going to have here as a matter of fact. So now we can use W net. So W net is the change in kinetic energy. W net is the change in kinetic energy. Can you use that? Okay, or if you don't want to use that, you can use work done by non-conservative forces equal the change in potential energy plus the change in kinetic energy. You can use one of these. So we shall use W net first. Right, so in the first case, W net at this point, as this is actually pulled up, you'd have the work done by the weight plus work done by friction plus work done by the applied force is half m open bracket V final squared minus V initial squared. So which means the work done by the weight is mg sine theta delta x cosine theta, which is work done by friction, work done by the applied force, is half m V final squared V initial squared. We substitute the mass. It's a 20 kilogram crate, so you put 20, open bracket 9.8, or yeah, 9,8 can do that. The sine of the angle here, 18 degrees. And then obviously we consider a couple of things that remain very, very important. Delta x. So now, and the distance between points A and C is 15. Point A and C is 15,6. So we're going to put here 15,6. Going to put 15,6 here times the cosine of cosine of 180 degrees, right? Plus 13,5. Okay, so let us continue now, which is work plus the work done by friction, which is right. So yeah, okay. We continue calculating the work done by friction. Yeah, I'm in class until 10. Please we can talk after 10 because I'm in class, my dear. Okay. All right. So which means that we continue here to find the work done by friction, and work done by friction is 13,5 times the required delta x, which is 15,6. Just note that 15,6 times the cosine of 180 degrees, that becomes the work done by friction. And then now we continue to put more numbers. And let me just remove these marks here. And now you then have plus 96,8 times 15,6 times which is the work done by the applied force, times the cosine of 0 degrees. Because this applied force, now you have this displacement is 15,6, and you are most certainly convinced that the motor exerts a constant force of this. So the applied force by the motor, which is 96,8 newtons, right? And then obviously the delta x is actually 15,6, but it's also in the same direction. So that now the angle between them is actually 0 degrees. So you're sort of adding these to that, adding 1, 2, 3, 1. So this one goes with this. For friction, it's the second one. Work done by the applied force is the third one. And this is then equal to half the mass, which is 20. And then you have Vf squared minus 0 squared. V final is 5,96 meters per second. 5,96 meters per second. Okay, that's what we have. So obviously at this point, what we then have is that we've used energy principles to calculate the speed of the crate when it reaches point C. And this is how we've done it. Think about it and make sure you understand it, but we just used W net. But now there are a couple of things that are very important. As this is being dragged up, you'd have a couple of things. So it's very important to have an idea of the forces acting on this, because then you have the weight, you have the normal force, right? You have the, right. So you continue. Right, so here you'd have the friction. You'd have the friction that's going straight down. You'd have the applied force that is upslope. And here that is why here you have the work done by the weight. And then you have the work done by friction. You have work done by the applied force. Okay, so these are the things that have been catered for, and therefore the result and the answer is exactly that one. Just to get the third point. The motor exerts a constant force of that instead of that. Now calculate the minimum average power dissipated by the electric motor to pull the crate from point A to point C, from A to C through a distance delta x of that much. So now we're looking at 5.3. 5.3. Right, to calculate the minimum average power, right? So this minimum average power, so you're going to say power average is equal to the force times the average velocity. Power average is 96,8. Power average. And then the average velocity. The average velocity. So the average velocity is as follows. We know very well from the previous calculation that we calculated the speed of the crate when it reaches point C. Right, so the speed of the crate when it reaches point C was found to be exactly what? Was found to be exactly 5,96. Now remember that this electric motor pulls a crate from rest at point A. So it was at rest here, and then it moves up to that. So it moved from rest to 5,96 divided by, which is the average velocity. So we divide that by 2. and therefore the average is 288, comma what? Comma 46 watts. 288, comma 46 watts, then which is the minimum average power dissipated by the electric motor to pull the crate from A to C. So obviously, I mean, there are a couple of ways to do this particular question, but this is surely the easiest way to do it. The easiest way to do it. So the minimum average power dissipated by electric motor to pull the crate from A to C is power average, which is 288,46 watts. Okay. Let's look at point 4. Draw a, okay, when the crate reaches point C, the rope breaks. When it reaches point C, the rope is cut. The crate continues moving up the inclined plane, comes to a stop at point D, okay? When the rope is cut, it continues up to this point, D, and then slides down the plane past point B. Draw a labeled free body diagram for the crate as it slides down the plane past point B. So which means, therefore, you're going to have the weight, and then now we just need a free body diagram for the crate as it slides down the plane past point B. The crate continues moving up. The incline comes to a stop. So when the rope is cut, by the law of inertia, it still continues and then slides down to stop here. Okay, now you need to draw a labeled free body diagram for the crate as it slides down the plane past point B. Okay, right. So a couple of things, but its weight is there. But understand that obviously we have the crate reaches, and whatever happens, and we know very well that there's been friction all the way. Right, a constant frictional force acts on the crate as it moves on the inclined plane. So you had 13,5 friction. So which means that there's going to be actually friction. There's going to be actual friction, and then it is like this, and this is the normal. This is the normal force. Remember, the rope is cut now. It's only friction that is opposing the motion. The weight is there and the normal force is there. And this is the actual free body diagram there. Right, next point. Okay, let's look at 5.5. Right, in 5.5, draw a velocity time graph for the entire motion of the crate starting from point A until it passes point B again on its motion down the incline. From A until it goes back. Let us look at that one. So we'd have the graph like this. So to draw the correct graph, you need to first look at something. The choose direction. Upwards is positive. Upwards is what? Is positive. Okay, if upwards is positive, then you're going to have this. So you're therefore going to have the time in seconds. Right, so it's going to be exactly like this, and then okay, we're going to discuss this is going to be actually then like this, and then it's going to be like this. And then at this point, can do it in green. Want to mark the velocity of 5,96 here. 5,96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . 96 . and that is velocity. Okay. This velocity is in meters per second. Okay. Now let's think together, please. You have to draw a velocity time graph for the entire motion of the crate starting from point A until it passes point B, again on its motion down the inclined plane. Right, so there are a couple of things, therefore, that are important. Let's analyze these together. Let's analyze these together. You would remember in our previous calculation here that we used the energy principles to calculate the speed of the crate when it reaches point C. When it reaches point C, it was 5,96. It was 5,96 meters per second. So that is why here it started from rest, but its velocity increased to 5,96. All right. And then now when it reaches 5,96 at the point, the rope breaks. When the rope breaks, we understand before that it still continued to D, so but its velocity dropped, reduced, and then it came to a stop at point D, then it stopped at point D, and then after it stopped at point D, it then started sliding back past point B. So this is sort of the velocity time graph for the entire motion of the crate. Right. Right. So you continue. We continue. Right. So this is the velocity time graph because it started at point A, it was at rest, and then its velocity increased. When it reached point C, it was at moving at 5,96, and then its velocity, but then the rope break and its velocity started dropping because the rope was cut and no longer actually there, no longer pulling it up, and then it then started reducing. It started slowing down and then came to a stop at D, and then it started sliding down, and then it passed point B like that. So this became sort of the velocity time graph there of the motion. Right. Let us look at the next question. The next question is about Doppler effect. Let's look at this question about Doppler effect. So Doppler effect is very, very important. A car moves at a constant velocity of 22 meters per second on a straight horizontal road towards a stationary device. Here's a car moving at 22 meters per second on a straight horizontal road towards a stationary device, which can both emit and detect sound waves. The device emits sound waves with a frequency of 24,000 hertz. These sound waves are reflected off the car, and reflected sound waves are then detected by the device as shown in the diagram below. State the Doppler effect in words. State the Doppler effect in words. And this is how we state the Doppler effect. We say the operand. The operand. This is called Doppler effect. The operand change in frequency. The operand change in frequency Right, apparent change in frequency of the sound. Of the sound detected. Okay, yeah, we can use apparent change in frequency. If you don't want to use the word frequency, apparent change in frequency, the sound, you can say sound or pitch, frequency or pitch. The apparent change in frequency or pitch, okay, of the sound, right, of the sound detected, right, detected by a listener because the source, and the listener because the source and the listener have different velocities relative to the medium of propagation. Medium of propagation. So the apparent change in frequency or pitch of the sound detected by listener, because the source A and the listener have different velocities relative to the medium of propagation. So this is Doppler effect in words. Once again, we repeat the statement. It is the apparent change in frequency or pitch of the sound detected by a listener because the source and the listener have different velocities relative to the medium of propagation. Now, in 6.1.2, we perform a calculation. So we're saying if the speed of sound in air is 340 meters per second, calculate the frequency of this, the frequency of the reflected sound waves detected by the device. Let us look at this particular question, 6.2. 6.1.2. So we're going to use the formula. The frequency detected by the listener is VVL divided by VVS. Oh, God. Right, so this one is going to be VVS. And then this one is going to be frequency of the source. And therefore, we perform further calculations, and we then say the frequency detected by the listener is the velocity of sound in air, which is 340, plus the velocity of the listener. Right, remember the velocity detected by the listener, because a car moves at a constant velocity of 22 meters per second on a straight horizontal road towards a stationary device which can both emit and detect sound waves. All right. So the device obviously continues to emit sound waves with the frequency of this. So this becomes the frequency of the source. But what is the actual velocity of the listener? Right. What is the actual velocity of the listener? And what is then the velocity of the source here as a matter of fact? I want us to look at these, but look at these very, very carefully, because they want us to calculate the frequency of the reflected sound waves detected by the device. So what is then happening here is that we are having the fact that this car moves at a constant velocity of 22 meters per second in a straight horizontal road towards a stationary device, which can both emit and detect sound waves. Okay, so this is, the device itself is what? Is most certainly stationary. So if it is then stationary, we're interested in calculating the frequency of the reflected sound waves detected by the device. So would note that, therefore, that at this point, the speed of sound in air is actually 340 meters per second. Right. Okay. Right. So we're interested in, therefore, knowing what is the velocity of the source. So now, if you are to actually now deal with the fact that this car that is moving at this velocity itself, we're going to associate the fact that the velocity of the car, which is this, we are interested in knowing the actual frequency that is detected by the listener here. If we agree that first things first, the source, the device emits sound waves of the frequency of 24,000 hertz. Right. And I want us to look at this very carefully, and we're going to put the velocity that is actually detected by the listener. Okay. Right. If we then say we are actually able to understand that you have the emitted waves by the device and the reflected waves. Right. So these reflected waves, you really can be in a position to note, therefore, that this car that is moving at 22 meters per second will result in waves that have a velocity of 22. Right. Or you would then say the velocity associated with the listener for these waves is actually 22 meters per second. The velocity of the speed of sound in air would then be 340. And if you use your calculator, you can put this one in brackets. Pay particular attention in this case because you have a couple of values here. Okay. Okay. We continue. We continue. So yeah, this is going to be 340, like that. So, which is, therefore, the frequency detected by the listener is going to be 25. If you use the calculator, 552,94 hertz. So that in the end, then, you then say the actual frequency detected by the listener is going to be VS divided by VL here, VS here. Okay, let's put VL here, VL here, VL here. And then we have FS here. Right, so, which means, therefore, the frequency detected by the listener, frequency of the sound detected by the listener, is going to be sitting at, now, this is going to be exactly 340 divided by 340. And therefore, because this car moves at a constant velocity on a straight road and towards, because it is towards, this is going to be minus. Right. This is actually going to be minus 22. That's the velocity of the source. Right, it's going to be actually minus 22 is the velocity of the source. And therefore, it is multiplied by this particular frequency, which is 25, 552.94. Then if you use a calculator, you'll be able to realize therefore that this is 27,320.75 hertz, like that. So that now, because there's calculate the speed of the frequency of the reflected sound waves detected by the device, so those will actually therefore be 27, will actually become 27, right, 27,320.75 hertz. Okay, yeah, we apologize there because number show was a little bit cut. Then, yeah, without wasting time, we'll move to one more question. The last question, the spectral lines observed for a distant star, right, the spectral lines observed for a distant star show that the star is moving away from Earth. Okay, if the star is moving away from Earth, right, explain by referring to frequency how one can deduce that the star is moving away from Earth. Okay, we need to use explain by referring to frequency. So we need to explain using by referring to frequency to deduce that the star is moving away from Earth. So we note that the frequencies, right, the frequencies of the spectral lines, the frequencies of the spectral lines would have decreased, right. Or if you don't want to say this, you can say the spectral lines from the distant star, the spectral lines from the distant star, okay, let me just finish this off. From the distant star are shifted towards lower frequency. Towards lower frequency end of the spectrum. Right, the frequencies of the spectral lines would have decreased, or the spectral lines from the distant star are shifted towards lower frequency end of the spectrum. So obviously we're saying the spectral lines observed for a distant star show that the star is moving away from Earth, explained by referring to frequency, how one can deduce that the star is moving away from Earth. The frequencies of spectral lines would have decreased. So a decrease, if the frequencies decrease, it means the star is moving away from Earth. It means that the star is moving away from Earth because the frequencies decrease. That's how we can use frequencies. So you look at the frequencies. If the frequencies decrease, then you can say the star is moving away from Earth. Or alternatively, you can say the spectral lines from the distant star are shifted towards lower frequency. Because the frequencies decrease, you can say the spectral lines from the distant star are shifted towards lower frequency end of the spectrum. So lower frequency end of the spectrum just signifies that the star is moving away from Earth. Any question? Right, we've done enough for today. Thank you guys for joining us. I'm gonna make the video available for tonight. Okay, so yeah, thank you for joining us, and I'll keep you posted on the group because I want us tomorrow at 8 p.m. to do mathematics. Tomorrow at 8 p.m. to do mathematics, y'all. So stay ready. Stay ready. Okay. Stay ready. Stay very, very ready. Yo, from us, guys, have a good evening. Until tomorrow at 8 p.m., have a good evening.